So I apologize, I got interrupted in that problem. But we can continue on solving it now. So we've got the, like I said, we know the Ka for acetic acid, we know the Kw, so then we can just solve for the Kb. That gives us 5.55 times 10 to the negative fifth. I'm sorry, 10 to the negative 10th. And that is our Kb for number, for the conjugate acid of C2H3O2 minus. Now what we have to do is compare that to the other reaction, OCl minus. So we've got OCl minus, that's going to react with water, and that's going to produce HOCl plus OH. Okay. So this is a weak acid, and they tell us the Ka for this weak acid is 3.5 times 10 to the negative 8th. We'd like to know the Kb for the OCl minus. So Ka times Kb is equal to Kw. So we can solve for the Kb, 3.5 times 10 to the negative 8th times Kb, 1 times 10 to the negative 14th. So that means my Kb for the OCl minus is going to be 2.85 times 10 to the negative 7th. Compare that with the Kb for the acetate, which was 5.55 times 10 to the negative 10th. Well, who's got the bigger Kb? The OCl does, so this is the stronger of the two bases. Okay. Number 117. Determine the OH, H, and the pH of each of the following solutions. So we've got potassium, 1 molar potassium chloride. Okay, so this one is an easy one because, like I said, pretend it's a double displacement reaction. That would give us potassium hydroxide plus HCl. So guess what? The solution's neutral, which means the pH would be 7, and therefore the concentration of H plus will be 1 times 10 to the negative 7th, and the concentration of OH would be 1 times 10 to the negative 7th. So that one's easy. But B, a little bit trickier. Start another page for B. So we've got potassium and water. The trickiest part of problems like these, and this is going to transition into chapter 15, is figuring out the relevant reactions. Okay, I wrote that way too big, so I'm going to rewrite it down here.
Where's Alina? She's still on her room,
So K C2H3O2, when we react with water, there's, like I said, pretend it's a double displacement reaction. You end up with potassium hydroxide and acetic acid. Well, what do we know about potassium hydroxide? We know that that's a strong base. That's why I said, unless you have the strong acids and the strong bases memorized, you're not going to be able to pass chapter 14 and 15. You've got to have that memorized. This is a weak acid, okay? So we're not going to care about the strong base because what's that going to do? The strong base is going to just break apart. So technically a strong base isn't actually formed, okay? So what's going to happen with this guy? Like I said, the potassium is not going to react with water. It's not going to do this because that would break apart anyhow. Okay? But the anion, the acetate, that is going to react with water. And it's going to produce acetic acid plus OH. So doing the double displacement, that helps us see that the solution is going to be basic. Whoa. Why? Because strong base. So that helps us figure out if it'll be basic or acidic. What it doesn't help us do is actually find the actual pH. To find the actual pH, we need to recognize that this is the reaction that's happening, that actually the OH is being created by the acetate reacting with water. Okay, so this is our actual reaction that's occurring. So C2H3O2 reacting with water produces this. Okay. Once you have the correct reaction, then solving the rest of the problem is actually fairly easy. So you've got an ice table. You know that the concentration is 1 molar. You've got 0 of this to 0 of this. I'm going to shift right. Okay. Rewrite our equilibrium expression. KB is equal to over okay. So this is going to be x squared. I want a little bit more space here. X squared over 1 minus x. But where do we get the KB from? Okay. Well, we know the Ka of acetic acid is 1.8 times 10 to the negative fifth. Okay. Well, to find the Kb, the Ka times the Kb is equal to the Kw. So what we can do is take the Ka for acetic acid and then solve for the Kb. And the Kb is going to be 5.5 times 10 to the negative 10th. So now we've got the Kb this x is too small, so then we can solve for x. And that gives me 2.3 times 10 to the negative fifth, and that's the concentration of hydroxide, okay? Now that we know the concentration of hydroxide, now we can find the pOH. That's going to be 4.63. And therefore the pH is going to be, because we know the pH plus the pOH has to equal 14. That means the pH is going to be 9.37. And then we want to do a check on this. If we go back, in the beginning, we said our solution should be basic. Well, is our solution basic? We got a pH of 9.37, so yes, our solution is basic. And again, this is what you would do if you had a salt in water to calculate its pH. Number 121. So we add sodium azide to kill bacteria in water, calculate the concentration of all species. Ooh, this is a fun one, in 0.010 molar solution of sodium nitride. So here's our salt, okay? It's going to break apart, and it's going to give us this and a very strange form of nitrogen. Okay. Now, which reaction is the important one? Is the sodium going to react with the water? No, because it would just give us a strong base which would break apart. So that's not the right reaction. So what about this guy? Will that react with water? Yes, it will. And that's going to give us this strange acid and OH. So our solution is going to be basic. It's basic one of two ways. You could look at it as we're producing OH here, or you could look at it as, you know, the quick and down and dirty way is like, oh, that's a strong base. But technically, this is not happening. This is where the OH comes from. So we do our ice table. N3 is 0.010 molar, 0 of this, 0 of this, minus x plus x plus x, 0.01 molar, minus x, 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 and then my Kb expression is going to be HN3 over OH minus over N3 minus. Okay. Now, where am I going to get that Kb from? Did they give it to us? No, they did not. They gave us the Ka of the HN3. So I'm going to have to calculate my Kb from this. This is 1.9 times 10 to the negative fifth. Therefore, the Kb of this, we're going to calculate from Ka times Kb is equal to Kw. So 1.9 times 10 to the negative fifth times Kb, 1 times 10 to the negative 14th. So then Kb is 5.26 times 10 to the negative 10th. Now that I got my KB, I can go back up here. Actually, it's probably easier if I rewrite it. So 5.26 times 10 to the negative 10th is equal to x squared over 0.010 molar. Solve for my x. This x is too small, so then another good thing about doing these problems on Notability is that you can always go back and listen to them. So if you're having trouble sleeping at night, you can always just replay my audio and have my nice soothing voice put you to sleep. All right. So that's going to be the concentration of my OH, right? They want the concentration of all species. So we need to find the concentration of H+. So the concentration of H+ is going to be 4.36 times 10 to the negative 9th. But that's not all of the species yet, right? This is also the concentration of the HN3. But there's one thing that we are missing yet. Actually two things that are missing. The concentration of the N3 minus is 0.10 molar. Why didn't this concentration change at all? Because the X was too small in comparison to that. So subtracting X from 0.10 molar doesn't actually change the concentration of the N3. But there's one more species out there that we need to know the concentration of, and that is the sodium ion. So because it was a salt, remember in the very beginning, the salt broke apart 100%. So that means that the concentration of this is going to be 0.10 molar as well. Okie dokie.